Hello, this is another physics video following Young and Freedman's University Physics. We are in chapter 21 on electric fields and such, electric fields and electric charge. And the fifth section is on electric field calculations. And this is, I think, it's hard, I can't remember anymore. I think this is the third of the videos in this series. We did one video introducing the concept of electric field calculations, and we did a dipole example there. Then we did a previous video about a ring of charge and what would be the electric field at a point, X away from the ring of charge. And in this video, we want to do an example. I think it's like, I don't know, 2111 example, something like that, of a line of charge. So you've got a line here, a line of length 2a. So this, I didn't draw it perfectly. So this point is supposed to be from the midway point. So this is supposed to be like 0 and then negative a and positive a in terms of distance, right? With little infinitesimal increments of dy, thinking this is the y-axis. So this is supposed to be halfway. So if this is a and this is negative a, then this length of this line of charge is 2a. So a line of length 2a has a total charge of q that's evenly distributed, which means that for some infinitesimal unit of dy, there is an infinitesimal charge of dq, which again is not Dairy Queen. So what we want to find is what is the electric field out here at point P that's x distance away from the center of the line. R represents, basically the hypotenuse of a triangle from wherever we are on the line. X is again the distance to the point, and alpha, or the little fishy, is the angle here. All right, so we've got a sense of what the problem is. Let's do it. So in the very first video on this section, we talked about linear charge density, which is symbolized by the Greek letter lambda. Okay, that's an L in Greek, believe it or not. So linear charge is a one-dimensional, which we're talking about a line charge, so one-dimensional works. Linear charge density is basically charge per unit length. So if the total charge of this line, if the total charge is q and the total length is 2a, then basically the linear charge density is going to be q divided by 2a, right? So it's how dense the charge is. It's the charge per distance, right? Total charge divided by total length. So they wanted to get that concept into one of the examples. Now, Q equals the charge density times the length, right? And so the infinitesimal charge is equal to the charge density times the infinitesimal length, right? And we just said that lambda is q over 2a, so let's substitute that in for lambda, and we have dq equals q dy over 2a. Okay, so we know this formula, right? From the previous examples, if E equals this q over r squared, then d equals this dq over r squared, right? This is a formula from field, what the field formula is. So let's go ahead and do some algebra and more. So if dq equals this, let's go ahead and substitute it. So there's the q, there's the dy, there's the 2a. And then for r squared, just to get a sense again, r squared, a squared plus b squared equals c squared. So x squared plus y squared equals r squared, right? So coming back here, r squared is going to be x squared plus y squared, right? X squared plus y squared. So you see how this, ask me questions. Well, okay, put it in the chat. So this is, everybody with me? Not too hard yet. Now, the x component of the field, the y component is going to cancel out because the top of the rod, or the top of the line, is going to be in the y direction down, and then the bottom of the rod is going to be in the y direction up, and so basically they'll cancel out. So the y's because of symmetry, cancel out, life is good, love that. So we only have to deal with the, now they actually do in the example in the book, play it out and show you mostly that the y's cancel out. Even if you do the math, we're not lying to you, the y's cancel out. But it's going to end up being the x primarily. So the x component of the field is infinitesimal field times the cosine of A. Why? Cosine of alpha. Why? Because we're trying to find the x component of it. And so the cosine of alpha is the adjacent over the hypotenuse, right? And so when we multiply the total magnitude times the adjacent over the hypotenuse, we're going to be left with the x component. Okay, we did this in a previous example and we've been doing it for a long time. So the cosine is going to equal x over the hypotenuse. And remember, this is the hypotenuse. We rewind the video. Okay, so put it all together. And so this is dE, and this is cosine of alpha. So multiply this times this, and what we get is a monstrosity. Again, okay, just breathe. This is not that hard. The bigger they are, the harder they fall. This is just simply taking those two things and scrunching them together. And so when you multiply this to the first power times this to the half power, it's 1 plus a half, which is 3/2. So that's where the 3/2 bit comes from. All right, with me so far? Now, if we want to know what the total for all of the little infinite, if you add up all the infinitesimal little field charges of the line, you add them all up, that's going to be the integral from negative alpha to alpha of all this stuff. All right. Oh, now's the semi-hard part, or at least almost. We're not quite there yet. So first of all, a lot of this is a constant. The x is the distance that the point is out. It's a constant. I almost wish that they hadn't put x, but it's a constant. So x is a constant, x squared is a constant, a is the length of the rod. It's a constant. Epsilon 0 pi is a constant, and the charge is constant. So a lot of this is a constant and comes right out. And so the part that we can't pull out of the integral is this dy over x squared plus y squared to the 3/2 power. Even though x squared is a constant, it's connected to the variable y, and so we can't pull it out. It's stuck. You know, it's like, no, come back for me. Anyway, so let's go ahead and integrate this. This is quite a challenge. I went ahead and did it. Oh, let me just clarify something I did. You don't have to do this, but I changed it from 0 to a. I didn't have to, and then doubled it. It's going to be the same amount, but you know, rather than have to do two subtractions, just by pulling the two out, it gets just a teeny bit easier a little bit later. Okay, it would have come out the same way if I'd have left it negative a till negative alpha to alpha. Okay, so this is the part here. Let's take some time. Let's take some little time away and look at this integral part right here and figure it out. And then we'll come back and throw this back in. But for the moment, I'm going to take it out just so that we can look at this one little part. Okay, now what he says is, to the integral tables. And so I did a Google search on integral tables. And I looked through page after page of integral tables. And I finally found this. This is an integral table. What is an integral table? It's basically somebody sat down and shown you how to integrate certain things. And so the one I found basically says, again, I'm not going to prove this. It was just in the integral table, that the integral of dy over x squared plus y squared to the 3/2 power equals y over x squared times the square root of x squared plus y squared. I'm not going to prove that. I'm not going to justify it. I'm just going to say this was on, I found it on the internet, okay? So I can, but notice that this is exactly in the form of this. And so let's go ahead and do it. Let's do it, baby. So basically, the integral of this is going to end, so putting in the particulars, and again, from put in the alpha and then minus 0, because when you put in a 0 for y. It's 0. 0 divided by anything is 0, except for 0 divided by 0, but it doesn't come out that way. So when I plug in alpha, I end up with yeah, I end up with this. So okay, so now we know what the integral of this monstrosity is. It's this. So now I can go back and put in that front part again that I set aside, for a rainy day. And so EX equals this times this, and I see some stuff that will cancel. The 2's will cancel. The A's will cancel. And so I'm left with this answer, which is the answer, surprisingly, that they have as well. So all that remains is for us to put it in vector form by putting the I unit vector there. And we basically are saying that all that we have is the X, component, or the I dimension vector is what results. That's what's at that point. At that point of the electric field, the vector of the electric field is this. All right. Well, hopefully that wasn't too painful. One more example in this section, and we'll move on to the next section of Young and Freedman's University Physics.